welcome back to our new video. Okay, eyes on the board. Look at these numbers. 2, 2, 1, 1, 1, 2, 2. 7 numbers, and one number appears more than half the time. Finding it sounds easy, right? We can just count everything. But see, what if I tell you we can find that number without storing the frequency of every element? No hash map, no extra array, just one candidate and one count. How can that possibly be enough? Before we reach that, let's understand the question properly. We have this array 2, 2, 1, 1, 1, 2, 2. Our job is to find the majority element. Now, what does majority mean here? Very simple. A number that appears more than half of the total elements. Here we have 7 elements. Half of 7 is 3.5, so the majority must appear at least 4 times. Now count the 2's. 1, 2, 3, 4. So 2 is our answer. Simple. But the answer is not the interesting part. The interesting part is, how do we find it efficiently? Because in a small array, counting looks easy. But when the array becomes very big, we need a better way to think. Okay, now you solve it first. Suppose I give you 2, 2, 1, 1, 1, 2, 2. You already know the answer is 2. Forget the answer for a moment. Think about the method. If this array came in an interview, what would you do first? Maybe pick one number and count how many times it appears, or store the count of every number somewhere. Think. Don't worry about the best solution yet. Just tell me, what is the first correct approach that comes to your mind? Okay, most of us will start by counting, and that's completely fine. So let's start there, and then see where the problem begins. Okay, we said the first idea is pick a number and count how many times it appears. So let's actually do that. Our array is 2, 2, 1, 1, 1, 2, 2. Total elements, 7. So to become majority, a number must appear more than 3 times, basically. At least 4 times. Let's start with the first number, 2. Now count every 2. First element, 2 match, count become 1. Next, 2 match again, count 2. Next, 1. Not a match, count stays 2. Next, 1 no. Still 2. Next, 1 again. No. Still 2. Next, 2. Yes. Count becomes 3. And the last element, 2. Yes, count becomes 4. 4 is greater than 3. So 2 is the majority element. Done? For this example. That looked easy, right? But notice what we actually did. We picked one number, then walked through the complete array. And if that first number was not the majority, we would pick the next number and scan the array again. Then maybe the next one, and scan again. That's where the problem starts. Now let's write exactly that idea. Nothing clever yet? First, we get the size of the array. N equals len open parenthesis nums close parenthesis. Now go through every number. For num and nums colon. For each number, start its count from 0. Count equals 0. Then again, go through the complete array. For x in nums. Now compare. If x is equal to our current number, increase the count. If x equals num, count plus equals 1. And after counting, we check. Did this number appear more than half the time? If count greater than n//2, return num, that's it. The code is simple. And it works. But see the issue. We have one loop inside another loop. For every number, we may scan the whole array again. That repeated work is what will hurt us. Now, let's see how expensive this can become. Suppose the array has 50,000 elements. Sounds manageable, right? But our brute force approach can do roughly 50,000 times 50,000 checks. That's around 250 crore checks. 250 crore for one array. So this approach, O of n squared, and that's the problem. The code is correct. The idea is easy, but we keep counting the same numbers again and again and again. So think about this. If we already counted a number once, why should we count it from scratch the next time we see it? Can we remember the count instead of repeating the work? Yes. And that's where our next approach starts. Okay, our brute force problem was simple. We were counting the same numbers again and again. So now, instead of forgetting the count, let's remember it. We can use a hash map. Our array is 2, 2, 1, 1, 1, 2, 2. And initially, our map is empty. Our total elements are 7, so majority means more than 3. Basically, we are looking for a count of 4. Let's start. First number, 2. Is 2 already in the map? No, so add it. 2 to 1. Our map is now a 2, 1. Next number, again 2. Is 2 already there? Yes, increase its count. 2 to 2. Map becomes 2, 2. Still not more than 3. Move ahead. Next number, 1. Is 1 in the map? No, so add it. 1 to 1. Now, 2, 2, 1, 1. Next number, again 1. Already there. Increase the count. 1 to 2. Now, 2, 2, 1, 2. Next, another 1. Increase again. 1 to 3. Now, 2, 2, 1, 3. Still not majority. Next number, 2. Its current count is 2. Increase it. 2 to 3. Now, 2, 3, 1, 3. Still not enough. Last number. 2. Increase again. 2 to 4. Now 2, 4, 1, 3. And 4 is greater than 3. So we can stop. Our majority element is 2. See the difference? Before, for every number, we were scanning the complete array again. Now, we visit each element once and remember its count. No repeated counting. Much better. Now let's write that. First, create an empty frequency map. Frec equals open brace, close brace. This map will store the number and how many times we've seen it. Now go through the array. For num in nums, for every number, increase its frequency. If the number is not already present, start from 0, then add 1. Fricnum equals fric dot get num 0 plus 1. See this line? This removes all that repeated counting. Every time we see a number, we update its count immediately. Now after updating, check one thing. Has this number appeared more than half the time? If fricnum greater than lennums / 2, return num. If yes, that's our answer. And because the problem guarantees a majority element exists, we will definitely find one. So compared to brute force, this is a big improvement. One pass. No repeated full array scans. Now this solution is good. Actually, very good. Time complexity? O of n. We go through the array once. So speed is no longer the problem. But look at what we are storing. For every different number, we may keep one entry. Inside the hash map, if all values are different, the map can grow, almost as large as the array. So extra space, O of n. Now here's where the problem becomes interesting. Can we keep the same O of n time but remove this extra memory? No hash map, no frequency table, no sorting, just constant space. At first, that sounds impossible, right? Because if we are not storing the counts, how will we know which number appears the most? But see, the problem gives us one very powerful guarantee. The answer is not just the most frequent number, it is the majority. That means it appears more than half the time. And that changes everything. Think about it. If one number appears more than half the time, then all the other numbers, even when combined, are still fewer than that number. So what happens if one majority element and one different element cancel each other, and we keep doing that again and again? Will the majority disappear completely? No. Something has to survive. And that idea is exactly where our optimal solution begins. Okay, before code, forget candidate, forget count. Just look at the numbers. 2, 2, 1, 1, 1, 2, 2. We know 2 is the majority. Why? 4 2s, 3 1s. Now imagine, whenever we find two different numbers, we remove both. 1 2 and 1 1. Cancel them. Again. 1 2 and 1 1. Cancel. Again. 1 2 and 1 1. Cancel. Now what is left? 1 2. That's important. The other numbers tried to cancel the majority, but there were not enough of them. Because the majority appears more than all the other values combined. So something from the majority has to survive. Good. But obviously, we are not going to actually delete elements from the array. So how do we simulate this cancellation? With just two things, a candidate and a count. Think of count as how many votes our current candidate has left, not total frequency. Just the current vote balance. Let's trace it slowly. Start array, 2, 2, 1, 1, 1, 2, 2. Initially, we have no candidate, and count is 0. Candidate equals, count equals 0. First number, 2. Current number is 2. Count is 0. So nobody is winning right now. That means this 2 becomes our new candidate. Candidate equals 2. Now current number matches our candidate. So give it 1 vote, count equals 1 done. Second number, 2, next number, 2. Our candidate is also 2. Same number. So 1 more vote. Count equals 2. Candidate stays, 2. Third number, 1 next number, 1. Candidate is 2. Different. So they cancel 1 vote. Count goes from 2 to 1. Count equals 1. Candidate is still 2. Fourth number, 1 next, another 1. Again, different from our candidate. So cancel 1 more vote. Count goes from 1 to 0. Count equals 0. Now notice this. The first 4 elements were 2, 2, 1, 1, 2, 2s, 2 1s. Perfectly balanced. Nobody survives. That's exactly what count 0 means. Fifth number, 1. Now we reach 1, count is 0. So we start fresh. This one becomes the new candidate. Candidate equals 1, it gets 1 vote. Count equals 1. Sixth number, 2 next number, 2. Candidate is 1. Different. So they cancel. Count becomes 0. Count equals 0. Again, no surviving vote. Seventh number, 2 last number, 2. Count is 0. So this 2 becomes our new candidate. Candidate equals 2. And it gets 1 vote. Count equals 1 array, finished. Our final candidate is 2. And that's the majority element. Now see what we did. We never stored 2 to 4, 1 to 3. We never needed the full frequencies. We only kept track of who is currently surviving and by how many votes. That is the idea behind the Boyer-Moore voting algorithm. One pass, two variables. That's all. Now that the cancellation idea is clear, the code becomes very small. First, we need a candidate. Candidate equals none, and we need the vote balance. Count equals 0. Now go through every number. For num in nums, first check, is our count 0? If count equals 0, if yes, our previous candidate has no surviving vote left. So the current number gets a fresh chance. Candidate equals num. Now compare the current number with our candidate. If both are same, give the candidate one vote. If num equals candidate, count plus equals 1. Otherwise, this number opposes the candidate. So cancel one vote, else count minus equals 1. That's it. Look at this carefully. Same number, plus 1, different number. Minus 1 count becomes 0. Next number becomes the new candidate. That is the complete algorithm. And after one pass, return the candidate. See how small the code is? But don't memorize these lines. Remember the reason. Different elements cancel each other. The majority cannot be fully cancelled. That's why this works. Now there is one mistake. Students make a lot here. You may look at this variable, count, and think, okay, count means how many times the candidate appeared. Sounds reasonable, right? But that's not what this count means. Let's check. Take 2, 2, 1, 1. Actual frequency of 2 is 2. Now run our voting idea. First 2, count equals 1. Second 2, count equals 2, then 1. Different. Count equals 1, then another 1. Different again. Count equals 0. Wait. Frequency of 2 is 2, but our count is 0. So clearly, this is not frequency. The better way to think is, count is the vote balance. How many unmatched votes for the current candidate are still surviving? That's all. And there is one more question. What if the final candidate is not actually a majority? Good question. Normally, Boyer-Moore gives us a candidate. If the problem does not guarantee that a majority exists, we should scan the array one more time and verify its real frequency. But in this problem, LeetCode tells us the majority element always exists. So here, we don't need that extra verification pass. We can directly return the final candidate. Okay, now compare all three approaches. First, brute force. For every number, we may scan the whole array. So time, O of n squared, extra space, O of 1. Then HashMap. We visit every element once. So time, O of n, much better. But we store frequencies, so extra space can become O of n. Now Boyer-Moore, again, one pass through the array. So time, O of n. But how much extra memory? Just one candidate and one count. So space, O of 1. That's our best solution. But the real lesson is not the name, Boyer-Moore. The real lesson is this. If one value appears more than half the time, then that value appears more times than all other values combined. So when different values cancel each other, the majority cannot disappear completely. Something from it has to survive. Remember this line. Majority is stronger than everyone else combined. And when you see that kind of guarantee, think about cancellation, voting, balance, not always frequency counting. Now try these three next. Majority element 2, LeetCode 229. Find the duplicate number, LeetCode 287 single number. LeetCode 136 different techniques. but all three will force you to think beyond. Just store everything. That's the habit we want.